Welcome to our keynote about communication models and protocols, syntax, semantics, and pragmatics. Once again, we have the Best Question Award. So I would like you to participate. Any question and comments are more than welcome. We have a prize for the best question asked. So think about what you'd like to know about communication models, and we'd love to hear that in the chat. Our speaker is one of the first to talk beyond technical problems in communication. It all started with a presentation at 2019 Semantic Summit about semantic communication towards 6G. And he recently wrote a 3 times the usual size, so a very comprehensive paper about timing aspects towards 6G communication. Petar, Popovski.
Thank you, Kel. Thank you for the invitation.
Yeah, thank you for being here. And let's talk about your background. What's on there?
My background is some research discussion we had with my researchers, and I think in the heat of the discussion, now nobody understands what was written there because it's several several combined discussions. But I think we'll figure it out in the end.
Okay, well, let's talk about communication models. Have fun.
Yes. Thank you. Excellent. Okay, thank you. So in the next 35 minutes, I'm going to talk about communication models and protocols, syntax, semantics, and pragmatics. And this is the outline of my talk. I'm first going to give some context about 6G and why it's interesting that the communication is moving beyond the technical problem, beyond the syntax. Then I'm going to talk a little bit about the significance of time as we are moving towards 6G communications. And this is some discussion that already started in 5G, but now it's being significantly expanded. Then talk about syntax and semantics in protocols, and finally about pragmatics and timing performance. So, as many of you know, 5G systems were about communication, but not only increasing the rate, but expanding communication along 3 dimensions, usually represented by this triangle of eMBB, broadband, URLC, ultra-reliable low latency, and massive machine type communication. And the idea was that this can represent, the combination of this can represent any type of communication that we might need in the future. But it's not only about communication in 6G, because 6G is going to augment the normal domain of communication systems to go beyond communication. And this triangle is going to be augmented to include localization, positioning, and sensing. And all of these will be glued together with intelligence and learning. And you can say that now what was the concept of slicing, sharing the spectrum between different services in 5G, now will generalize to concept of slicing, sharing different types of services and information acquisition modalities within the same spectrum. And as Kjeld mentioned, back in 2019, we thought with my colleague Osvaldo Simeone about what is beyond 5G. And we thought that beyond the technical problem of communication, we might look into the semantic aspects. But to understand them better, we have to look into the 5 language domains, which is, linguistics is much more traditional, mature, let's say, area if we compare it to communication engineering. So this is some area from which we can learn. And the 5 language domain which are known are phonology, which is basically studying the speech sounds. Then there is morphology, where it's studying the morphemes, the basic units that have some meaning, minimal meaningful units. Then there comes the syntax, which is about rules for forming sentences and combining words. Then there is semantics, about what is the meaning of the combination of words. And then there is pragmatics, which says how the language is used and what are the rules for conversation and in a given social context. So towards achieving certain goal of the conversation or similar. And then we can make part towards this with communication systems, because phonology corresponds to physical layer, transmission of symbols, where a symbol is not the meaningful unit of a communication, because the meaningful unit of communication becomes packet, which corresponds to morphology. And then the next step is the syntax, which is corresponding to control information, whether the packets are correct, whether we are in a state where we need retransmission, acknowledgement, or so on. And then in communication systems, we are leaving out the last two parts. And this is the motivation to consider them as we are moving towards 6G systems, because the problem of reliable communication on the noisy channel becomes less and less relevant, and we are becoming better to do that. But what becomes more relevant is which data we are sending and how we are using that data, right? And this is a problem which was also noticed by Shannon and Weaver in their paper from the 60s, where they defined technical problem as the only problem which is of interest for communication engineering. And then on top of that, they defined the level B problems, which are semantic problems, and level C effectiveness problems. So this means that this void in the communication systems of semantic and goal-oriented communication corresponds to this level B and level C problems, corresponds to pragmatics and semantics in the five language domains. And the motivation in communication engineering to move towards that direction is to enable with limited resources, limited energy resources, and within limited time, to transmit reliably what is relevant and important information, rather than just transmitting information for the sake of transmitting into a communication system. And to do that, we need to look into what is the purpose of the transmitted data. And a good place to start with it is Internet of Things systems, IoT systems, where we can see an IoT device to be a microtunnel between the physical and the digital world, because as physical information through sensors is converted into digital data, while the data and algorithms are converting digital messages into physical actions. And the data can be used in three principal ways. One is learning and training of AI models. Second is inference and command actuation, or decision making. And the third one is storage of value. So we are storing the data with the hope that we can exchange it for a value, or we can exchange it for other data. Then another aspect towards 6G, which is relevant for this, is the aspect of intelligence, because one thing which is different from the previous communication systems is that the end nodes are going to have intelligence that is going to increase over time, because we see that machine learning model and AI are basically omnipresent in every aspect. So they're also going to be present into the communication protocols. And rather than having communication protocols that are designed once for all, we are going to have communication protocols that are evolving. And then another interesting thing is the value of the data in 6G, because we are having enormous data amounts that are used in various inference and learning tasks, and wireless links are transmitting every day zillions of bits. The problem is, what is the value of these bits within a given context, and how this value can be judged? One can think that in the future, the IoT devices might become autonomous sellers and buyers of data, right? Because we can have a camera which is collecting data, and the camera is capable to offer this data on a given market and get the monetary reward for that data. The question, of course, from ethical point of view is, why would you sell your data? And this is a legitimate question. But let's recall that today we have two dominant models of data. One is you give your data for free to the social media, and the other is you keep your data fully private under GDPR, or let's say with the companies that do not allowing your private data to be leaked and so on. What we are saying here is that as more data is generated, we might be able to find a compromise between the two, fully private and fully free data, and to start to price the data and offer a data within a given price, within a given inference, decision, or machine training of machine learning algorithm. So having said that, let's look into what is the significance of time as we are moving towards 6G. So the Shannon communication model, we think of it as a model put in time, but actually Shannon's communication model is not including time inherently, but is just showing what is a causal representation among channel uses. So we're just saying which communication symbol is following another communication symbol. If we want to include time, which is a physical quantity, we need to specify a communication bandwidth. Once we specify communication bandwidth, then we can put a time structure. But nobody says that this time between two transmitted symbols should be equally spaced. We're just saying that they are occurring one after another. And the easiest way to implement timing structure is to put, of course, regular spacing. So this is just to clarify what is the time in communication model. So if we want to have time in Shannon's communication model, we need to specify the bandwidth. So the assumptions behind Shannon communication model, which is, by the way, extremely powerful, is that there are some tacit assumptions. For example, that there is a instant message decoding, so we're not considering the delay, we're not considering the time for processing the message. There's no additional latency due to protocol interaction. Then the important from a semantic and pragmatic point of view is that the sender and the receiver are always ready, and the receiver is always interested in whatever the sender has to say. So that's the basics of this model. And data is always available. So this model is very suitable to treat the correctness of communication, the technical problem of communication. But for the full syntax, we need to include the control information or the protocol information. Adding of semantics and pragmatics requires change of the model, moving towards source coding and considering what is the final purpose of the transmitted data. So we can define semantic and effectiveness in relation to the three mentioned principal uses of the transmitted data. For example, joint source channel coding is related to reliable storage or exchange of data. In learning on inference, we can talk about what is the semantics of the data in the context of a certain trained model. So what is the meaning of the data for a given model that is being trained? And in effectiveness, we can couple the inference based on some data with the actuation that happens in the physical, with the actual physical action. So having said that, we can try to come to a simple criterion about what is the difference between semantic communication and pragmatic communication. So a possible way to differentiate is to use time as a differentiator. So in semantic communication, we are looking into non-real-time constraint. So we say t goes to infinity, and the real-time relevance of the transmitted information is low, meaning that the meaning of the data changes over a long period. And here we do not really need to specify the bandwidth because we have a piece of data that has certain meaning in a certain context, but that context doesn't change quickly within the physical world. Pragmatic communication, where we look into the real-time interaction, like conversation in linguistics, and the time goes to zero, meaning that that is an indication that we are looking into real time. And the meaning and the interpretation affects the physical actions that lead to a certain goal. And here we need to specify the bandwidth because without it, we cannot couple the communication to the real world. So when we go talk about semantics, we can define different measures such as semantic entropy and other measures that reside purely in a logical domain, or we can discuss about knowledge graphs. And furthermore, we can make relation to source channel coding, like is the work of Dennis Gunduz. And a good example in that context of a semantic problem beyond the traditional joint source channel coding is the problem of, let's say, image retrieval at the edge, where we are trying to retrieve the edge without having local access to the database. Then, in terms of pragmatics, we are going to see that there's a difference with this description of the communication setup. But first, let's talk about something that is more common in communication protocol, and that's the syntax. So to understand the meaning of syntax, let's look into the transmission of a wireless symbols, where we look at the one specific symbol, which is, for example, a QPSK symbol. This symbol doesn't have a meaning by itself. It cannot be interpreted without a context. To interpret it, we need to come to a minimal unit of meaningful data, which is the packet. And then to interpret that packet correctly, we need to receive a suitable control information. So from the communication protocol viewpoint, the control information is a part of a syntax, but brings local meaning of the packet. So at a given layer, the control information tells what is the meaning of the data within that layer, right? So, so that means that when we speak about semantics in communication, we are going above the usual protocol layers and think about the high-level meaning of the data, not the meaning of the data within a given protocol context. So, so in that sense, control information is a key for interpreting what has been sent in a packet, and but it's still not understood very well how to model this in a communication theoretic way. An example of how to treat control information, how to basically evade control information, is a recent paradigm in IoT, which is called unsourced random access. So all packets are created same code book. There's no possibility to address to put an address or device-specific information. So when we receive a packet, we can see what is the data of this packet, but we cannot interpret who sent this packet and to which, and potentially not even to which service it belongs. So here we have a syntactic deviation from normal communications because we are not putting address of the originator, so we don't know the data from where it is coming from, but we have to still interpret it. And you notice that they are selecting the data from the same codebook. So if, for example, you can say, okay, let's say that the node can include its location in the data. It cannot include it because we do not have a specific part where we can put location or address of the node. Just every node in the network is sending exactly the same type of information, right? And this leads to a semantic problem at the layer 2, because in which scenario we could use this communication paradigm, what this communication paradigm could be useful for if we cannot interpret who has transmitted the data. So we have done a work where we have shown that we could use other aspects of the protocol to identify the users. And specifically, the problem that we have considered is the problem where we have an unsourced random access implementation, and we are sending completely random messages to it, so we cannot identify the user at the layer of the protocol, but still at the end we can identify the user. The reason is that we are using the shared secret keys for communication between the devices and the base station, and this shared secret key is going to generate a message authentication code, which by definition should be random. And if we generate that, we can remove the address from the node, because then the received signal, we can try to match the data with whoever has shared a secret key, and then based on the matching of the data, we can find which device exactly sent the data. So even without sending the syntactic information, we can extract and interpret the message based on other security information that has been shared a priori. This is one example of how syntactic deviation can still lead to efficient protocols and be interpreted properly. Another one is a work where we have considered to model a protocol as a state machine, which evolves and then transmits message within each state. So the normal way to do it is that every state is reflecting what is the protocol state is reflecting what is the control information that should be sent. This is the red thing. Then we are sending the data, and we are sending a parity, which is kind of parity check for the data and for the state. But what we could do is, knowing that the protocol is evolving through a Markov chain, we can remove the explicit state encoding and just send the data that is generated in each state. The control information can be shown that it can be inferred based on this sequence of messages which is sent from the source. So again, we are deviating from the syntax of the protocol, but we do not break the semantics of the protocol at that layer, because we can still interpret who is sending the data. Then a third one is a case where we make syntax purpose. So what we are doing is that we're having a random access by massive number of users. So there are many devices transmitting to the same receiver, and after the reception, we have to send acknowledgement to tell who has succeeded in transmitting. So what we are doing is we're using a limited number of bits to acknowledge the users. So rather than sending the IDs of the users that have sent the data, what we are doing is we are using a limited message in which we are encoding the users within certain B bits. But when we are encoding the users, because there are very few bits, we are not only encoding the subset of users that transmitted, but we are encoding also other users that did not transmit. So we can have two types of errors. One is the false positives, meaning that we are basically not decoding some users, but we are reporting to them that we have decoded them. Or false negatives, where there are users that have transmitted, we have not, but we have not decoded them, right? So the interesting is this false positive. How could we use it? The point is that, let's say that there are users 1, 2, and 3 transmitting, and users 4 and 5 are not transmitting. If I send acknowledgement that acknowledges the transmission of users 1, 2, and 3, 4, and 5, 1, 2, and 3 will know that their message was received. 4 and 5 will receive a message that their message was received. But actually 4 and 5 do not care because they didn't send anything, right? So looking into this broader context, we are capable to save bits and make efficient communication, even if we go, even if we make a syntactic error. So what we are trying to say is that the prior context can help us to decode the data correctly. And this here is showing how much we are saving if we allow these false positives. So if we allow false positives with a relatively high probability, for example, here 0.1, then we can actually send the data scales very slowly with a number of transmitting users. While if we concatenate the IDs of the users, basically the required data rate explodes for acknowledging the users. So let's come to the last part of pragmatics and the timing performance. So as I said, pragmatics of communication is considering a real-time communication, which, for example, in 5G was identified with what was called low latency and ultra-reliable low latency communication. And the approach in 5G was in some way a maximalist approach, because the idea was that we have a full latency budget for, let's say, compression, computation, transmission to the core network, and then 5G, we give just a little bit to that latency, which is often 1 millisecond only. But the total latency budget is larger than 1 millisecond. So the question is, why should we pressure the wireless part, which is in any case difficult to use because of the variability and stochasticity of the wireless part? Why should we pressure the lowest latency there if we could remove some of the latency consumption into the other part, right? Computation, compression, or the core network. And in that sense, latency is not the only measure that is important in communication, but in the past decade, we have seen a measure called age of information, where we are not looking into the latency of a packet from A to B, but we are interested in how fresh the packet is when it arrives to the destination. And the difference with the age is that this is interesting in tracking applications, where we want to find, for example, here is the location of an airplane, or some sense compute actuate cycles that are not sensitive to packet delay, but to the freshness of the information at the receiver. Then the age of information is defined as a measure which kind of increases in time, and when the new packet comes, the freshness comes down to the freshness of the new packet. So that's why it has this sawtooth form. And the key assumption is that the fresher information carries more relevance and has a higher effectiveness, which or is more pragmatic to send that type of information, because it gives a more meaningful picture of the current state of affairs. So, and these measures are not something that only academics have worked with. If you see what are the timing measures adopted in 3GPP, you can see that there's increased adoption of these more complex measures rather than just the latency. So like age of information and various derivatives. So one thing that we have done towards this pragmatics of communication is, instead of considering push-based communication, like in the original Shannon model, so push-based communication means that the transmitter decides when and what to transmit. We have considered this model, which are inspired a little bit by computer science, where we have queries, and these queries are leading to certain responses from the devices. So pull-based communication means that there is a receiver that is requesting a certain information, and this information is basically the moment of collecting information is decided by the receiver. And now the idea is that the transmitter should not always try to push the freshest information, but only try to optimize the transmission for when the query is arriving. For example, if we know when the satellite is passing, then just before the satellite passes, we can prepare the data, encode it, and transmit it. And this has a profound impact on how the system works, because if we optimize for the query age of information, then the freshness of the data measured at the query moments is much better compared to the usual case where we optimize for the average freshness of the data. Then this is showing that how better this is in terms of CDF. So and the next step would be not to look only into the moments of when a query is arriving, but to look into the query content. So here is an example where we took, this is an example of what is pragmatics in communication, where we have an edge node, which is where the remote server is sending queries to the edge node. And this edge node has to collect data from the sensor. But the edge node does not necessarily collect data from all sensors, because the edge node has just to respond as correct as possible query to the remote server. So in principle, if the edge node can predict what is the data of all sensors, it doesn't need to collect anything. But we can also consider the case where the edge node is collecting some data from the sensors just to update its model sufficiently, and then updates the model and sends it to the remote server. So what we have shown here is that the case where each sensor observes a noisy observation of a process, and then instead of minimizing the state of all sensors, we are minimizing a function of these sensors. It could be maximum function, average function, quantile function, and so on. And what we have shown is that if you adapt how you are collecting the data to the actual query that comes from the remote server, then with collecting very few data, you can correctly respond to the query, meaning that you should not respond to every query by collecting all the data from all the sensors, but it should be a combination of what we estimate about the sensors versus what data we collect from the sensors. So another very practical work of this pragmatic and goal-oriented communication we've done in collaboration with Bosch, where we are considering AGV vehicles, which are used in the industrial setting, and where the vehicle has a sensor and an actuator. So the sensors of the vehicle are sending data to the controller, and then the controller is sending command to the actuator. So here, instead of measuring the latency and the age of information when it comes to the controller, we are measuring the age of the loop, meaning that the device, the AGV, is sampling the data, sending it to get a command, and measures the time when the command arrives. So the time between the sampling of the data and the arrival of the command is a time of the loop. That's the age of the loop. So we have shown that for goal-oriented communications, you do not need to optimize the age of the individual packets, but actually you need to optimize the age of the loop. If we do that using machine learning, what we can show is that this reinforcement learning scheme is using very little bandwidth and still keeping the system stable. While if we put this 5G requirement of 1 millisecond latency for uplink and downlink, we can still control the system, but the amount of bandwidth that we need to use is overwhelmingly larger. So what we are saying is that if we would like to have a pragmatic communication, goal-oriented communication, rather than optimizing for the latency of the packet, we can optimize for the timing measure that is relevant for that scenario. This brings me to the conclusion. As I said, the 6G is en route beyond communication, and there is some search for meaning for 6G, but also search for meaning of the communicated data. And we need to look into the actual use of the transmitted data, which could be classified as learning, inference, or storage or exchange. I tried to show the relation between the 5 language domains and the Shannon-Weaver classification of communication problems. And I have shown how syntactic deviation in some protocols can lead to efficiency while not losing the semantics of that data at a given layer. And finally, I've shown several examples of pragmatics of real-time communication. If you would like to read more about this, you can check our papers and blogs on these topics. So here are some additional references. Thank you very much.
Thank you so much, Petar, Popovski. So if you have any questions, what would you like to know about communication models and protocols, please type them in the chat. Petar, we already have a few quite, for me, difficult questions, quite specific questions about a couple of slides, so we'll bring them up later. You also mentioned Internet of Things devices selling their own data. And I was really curious, can you give an example of which data they would sell and how that would look like?
Right now, if you're interested in some data, you have to put your own device to collect the data, or you have to purchase the data from somebody else that is collecting it.
Yep.
But now, for example, with the distributed ledgers and blockchains, we could have the data that the nodes that participate directly on the data market, and they can try to bid their data, and then in this market can automatically buy and enable buying and selling of the data, which could be, for example, used for training of a certain model. Let's say that you have a satellite data and you would like to train a model to identify pirate ships. And then you can actually buy this data on the market. But instead of having this data on the market packaged by some company, you can have that the satellites are directly participating through blockchain and making transactions with smart contracts where you can get the data.
Okay, so that would enable me to sell my own whereabouts for money as well to the highest bidder using this system.
It depends who is interested in your whereabouts and how much they are ready to pay.
Fair enough. Okay, now to the real questions. First up is Christian Schleger, and he had a question on slide 24. Why do you remove explicit state coding?
In slide 24. Yes, we are removing it because we wanted to see whether we could, in the same way, reliably decode the data without decoding the protocol. So we wanted to see whether we could decode the data correctly without encoding the protocol information explicitly, but just having it having a joint encoding. And this was actually leading to, I didn't show the results here, but this was leading to much better reliability of the system because we were not using part of the data to encode the state, but we're using all the data, all the channel symbols to encode, put redundancy for decoding that, and then infer to the hidden Markov process, infer what is the state transition, what was the control information. This is going to increase the latency, by the way, but the reliability is improving.
Okay, and his follow-up, how many bits do you intend to use for ACK?
In the examples I was showing, not in this. I guess it's not here. It's for this question slide still, or for the other one?
Because I don't know, to be honest. It's here a separate question.
Here we didn't consider acknowledgement, but on the other hand, in the other where we considered acknowledgement was the massive acknowledgement. So the number of bits are shown actually on slide 30, where we are showing that the total number of bits we are using for, if we have 2 to the 32 users, we are using around 10,000 bits for acknowledgement, for encoding the acknowledgement. Sorry, 10,000 bits if we do concatenation, but we use around 1,000 bits if we are just doing it in the way we are suggesting.
And then we go back to slide 26, because Ifyo Lua had a question on that. What cryptography principles or technology were used to generate the shared key between the user and the receiver to
We
locate the packet.
We have just used the standard 3GPP cellular. It was we have just used the hash functions which are used for message authentication code in cellular systems.
Okay. Reginald wonders, you have mentioned earlier in the talk that perhaps we can reach a compromise in two models, private versus free for data, where data can be priced and offered. How soon or later do you think this will be realized in public?
I cannot comment on that because that will depend how much companies will pick up on that. But there is already economists working on data markets for pricing data based on the value.
Okay. And another question by him, given the different models discussed, which correspond to language domains presented, which is considered or mature enough to be used commercially?
That's an interesting question because I think now there is a big excitement about semantic communication in 6G, and the commercial use of this will depend on whether semantic communication will become part of the standards of 3GPP. And at the moment, there is a skepticism in the industry how this could be integrated in the standards.
Yeah. Okay. Andoi wonders, could you elaborate on the optimization with RL scheme in terms of policies and rewards?
Sorry, once more?
Yeah. Could you elaborate on the optimization with RL scheme in terms of policies and rewards?
Yes. So it was that is probably related to the last part. So the policy the policy was about how to select the transmission based on a certain age of loop, and the rewards was based on how well the inverted pendulum. How well the inverted pendulum of the AGV was controlled. So how low the error was towards the target state.
Okay. I'm just checking if there are any new questions. There are not. So then it's time for the best questions. So I'll repeat the questions, and you get to pick which one was the best question.
I think I already picked.
Well, let us know.
It was the question about the encoding of the state, why it is useful. I mean, because that was a good observation about the encoding of the state. Why was it useful, and why to keep it implicit?
Yeah. So why do you remove the explicit state coding? That was a question by Christian Slager. So Christian, congratulations. There is one new question coming up on the final round. So Christian does win, but we do have one final question for you. Ifyalua, sorry, just remember this. Can predictive algorithms be used to organize transmission to offer the freshest data at the moment of query?
Yes. A simple question. But they can drop me an email, I can send them paper about it.
Okay, we'll do that. Thank you so much for your time, Petar, and your willingness to answer all these questions. And hopefully we see you back at a next conference. Thank you for now.
Thank you very much. Bye.